Okay there, advanced students of chemistry. This is the last of the third recordings in case we don't see each other for a while. So what we have here is a heating curve and, a vapor pressure diagram. I'm sorry that my copy is not so nice. I hope that yours is, the one that you're printing is a little bit better, but mine's not in very good shape. But what we have here is some diagrams that you just need to be able to read and then interpret according to the particle attractions. So if you remember, we have this substance that is starting at a temperature of 0 and it's increasing to a temperature of 40. Remember that these flat lines are where melting or phase changes occur, right? So we know that it starts out a solid, phase change occurs, and then it turns into the liquid, and then the liquid will boil and turn into a gas. So this is just asking you to look at this chart and record what you see. We can see that the melting point of this substance occurs at this portion. So the melting point of this substance is 40 degrees, assuming that's in Celsius. The boiling point is at 90 degrees. So one question I might ask you, since we know this is not water, because water melts at a much lower temperature, how do the particle attractions of this substance compare to the particle attractions of water? So if you think about that, higher melting points mean stronger particle attractions. So this is something that has a stronger particle attraction than that water is having, something stronger than a polar bond. Notice that melting point and freezing point, trying to trip you up here, those are the exact same thing. The substance melts and freezes at 40 degrees Celsius. Now this says, what is the enthalpy of vaporization? We can actually read this chart and get the numbers off of that. So this is where vaporization is occurring in this segment of the graph. So the time in minutes is going from 16 minutes to 26 minutes. That's a change of 10 minutes. And if we read the beginning of the paper, the very top, it says, this sample is being heated at a rate of 400 joules per minute. And the sample is a 10-gram sample. So if it's 400 joules per minute, we've got 10 minutes, 400 joules per minute. And if we want the enthalpy of vaporization, we want to solve that in joules per gram. So we'll take that and divide that by our 10 grams. And that tells us that the enthalpy of vaporization is 400 joules per gram. Why don't you pause the recording and take a minute to calculate the enthalpy of fusion. Fusion is another word for melting. That occurs in this portion of the graph. Okay, I hope you've come back. And this will be 160 joules per gram. Now, this is also asking you to use this graph to calculate the specific heat capacity of the liquid. We know that specific heat capacity is measured in joules per gram degree Celsius. So we want joules per gram degree Celsius. We need to pick some portion on this graph, doesn't matter which, where we can calculate the change in the heat and divide that by the mass of the substance and the change in temperature that occurred there. So certainly we don't want to do this along one of the flat regions of the graph. We want to do this somewhere where the temperature is changing, and really somewhere where it might be a little bit easier to read the graph. Why don't we just use this segment here? So we know that the time is going from 0 to 2 minutes. to reach that. So we have 2 minutes. 2 minutes times 400 joules per minute gives us a heat of 800 joules, and that's per 10 grams. And the change in temperature there went from 40 to 0, so that's 40 degrees Celsius. 10 times 40 is 400. 800 divided by 400 is, wait a minute, 200? 800 joules went from 0 to 2. 2 times 400 is 800. 10 gram sample. Yeah. What, 20 joules per gram degree Celsius? Double check my math, people. And then this next question says, where is kinetic energy increasing? Remember that kinetic energy is a measure of the average temperature. That's what kinetic energy is. So anywhere the temperature is increasing is going to be listed here. And that would be in segment 1 of the graph, segment 3 of the graph, and segment 5 of the graph. And then where potential energy is increasing, potential energy is stored energy. That's going to be in segment 2 of the graph and segment 4 of the graph. Okay, your vapor pressure curve. We have chloroform, ethyl alcohol, water, and acetic acid. So what might be helpful is to know what the formulas for these substances are. Acetic acid has a dot structure. It's CH3, COOH, C double bonded to O, single bonded to OH. Remember, that's what makes an organic acid. Water, of course, is H2O. Ethanol is an alcohol, CH3CH2OH. Chloroform is CHCl3. So if we look at our vapor pressure here, we can see that the vapor pressure at 80 degrees Celsius for acetic acid is a little over 200. For water is a little over 300. And the vapor pressure for chloroform and ethanol at 80 are way up there. So if we look at this, it says what substance has the highest vapor pressure at 50 degrees Celsius? So here's 50, right? Of course, follow that up. Vapor pressure is lowest for acetic acid, then water, then ethanol, then chloroform. So we can see that chloroform has the highest vapor pressure. And really what's important about this is, what does this mean in terms of the particle attractions? With the highest vapor pressure, that means the weakest particle attractions. And if you look at the dot structures, chloroform has no hydrogen bonding, whereas the ethanol does, and of course so does the water, and so does the acetic acid. And what does this say then about acetic acid versus water? Acetic acid has the lower vapor pressure, which means that that is a stronger particle attraction. So you've got hydrogen bonding that can occur anywhere There's a lone pair on those oxygens, which means that that is a stronger interparticle attraction. What's the boiling point of ethanol at 600 millimeters of mercury? So, boiling point by definition is when the vapor pressure equals the atmospheric pressure. So when the atmospheric pressure is 600 millimeters of mercury, we're going to look at this chart. 400 or 500 let's see, it doesn't want the normal. Oh no, at 600 millimeters of mercury, so that's like, this is 500, 600, we're looking for ethanol. So come on over here, here's the line. This is where vapor pressure and atmospheric pressure are equal to each other, and they're telling us the atmospheric pressure is 600. So that temperature is in between 60 and 80. It's a little bit higher than 70. I'm just going to put here 72 degrees Celsius. And then it says, what is the normal boiling point of chloroform? Remember that normal boiling points are measured at atmospheric pressure, which is 760. Here's the chloroform line. Drop that down. And that's going to be 60 degrees Celsius. A little bit less than 60, maybe 59. I'm going to put 60. So one other thing I might ask you is, okay, given this, where does carbon tetrachloride fall on here? So here we have CCl4, we have a tetrahedron, we have a nonpolar molecule, and here we have a polar molecule. Both tetrahedrons, one is nonpolar, one is polar. Think about why that is. Where would you want to place the carbon tetrachloride line on this graph? So think about that for a minute. And if you have thought about that, what we know is that the carbon tetrachloride is going to have a weaker particle attraction than the chloroform. So we might want to start up here and have the vapor pressure go something like that for the carbon tetrachloride. Without being given any data, it's harder to kind of put that in there, but that's what you're looking at with the vapor pressure. All right, one more graph, and this is your phase diagram. So this is a phase diagram for water. We have the triple point, we have the critical point, and this measures pressures versus temperatures. If we change the pressure, we can see that the melting temperature, that divider between solid and liquid, gets lower. So increasing the pressure decreases the temperature of melting for water. And then we can see that increasing the pressure increases the boiling point of the water, right? So that's the line between water liquid and water vapor. And then the critical temperature is the temperature above which it doesn't matter how much we pressurize the substance, it is going to remain a gas. So most of the time at normal pressures, we can turn something into a liquid, at normal temperatures, we can turn something into a liquid by pressurizing it. The critical temperature or point is the point at which, no matter how much pressure we apply, it is too hot to turn it into a liquid. And then here is a phase diagram for carbon dioxide. Notice it looks a little bit different. Notice how low the critical point is. So the these are the conditions under which Carbon dioxide can be a liquid, a gas, or even a solid. So we know that if we want liquid carbon dioxide, we would need a pressure above 1.1 atmosphere and a temperature between -56 and 31 degrees Celsius. So have to be 5 times the pressure of the atmosphere. And then the triple point is the point where all three phases of matter coexist. In this case, it is 5.11 atmospheres and -56.4 degrees Celsius. Okay, a little review on some diagrams you need to know.